Now, when we know what is the inverse matrix and how to compute such a matrix, let's have a look at a few properties. If we take a matrix, which is a square matrix with non-zero determinant, and compute the inverse, and then the inverse of this inverse, then we get the original matrix. This is a similar situation as if we have a function, and we find the inverse function to this function, and the inverse to this inverse. This is the original function. Also, if we take a matrix and we compute the transpose, that means we rotate along the principal diagonal, and then we compute the inverse of the result, then we get the same result as if we compute the inverse and transpose only after that. If we take a matrix and multiply by some non-zero real number, we get a new matrix, and its inverse is in this simple relation to the inverse of the original matrix. If the matrix is 2 times greater, then the inverse is 2 times smaller, in the sense that each element is divided by 2. In general, 1 over k times the inverse of the original matrix, assuming the real number k is non-zero. If we have 2 square matrices, we can consider the product A times B, which is again a square matrix of the same size, n times n, and its inverse is B inverse times A inverse. Well, it's not so obvious that we have to swap, we have to start with B and then A. Let's prove this. But before we do, let's finish this list of properties. If we compute the determinant of the inverse, then this is the reciprocal value of the determinant of the original matrix. Perhaps we can show this. So we have 2 matrices, A, B, and we want to find a matrix, let's call it capital X, such that the product is E. And we want to find a relation between X, which is the inverse to AB, to A inverse and B inverse. If we multiply by A inverse from the left, we get B X is A inverse E. But E times anything is this anything alone, so we have B X is A inverse. And similarly, we can move B from the left to the right when we multiply by B inverse from the left. Remember that multiplication of matrices is not commutative, so we must pay attention whether we multiply from the left or from the right. And if we multiply by B inverse, then this removes this B, and we have X is B inverse A inverse. That means the inverse to AB is again a product of the 2 inverse matrices, but in the reverse order. Well, and a few terminology. The following statements are equivalent. That means if one of them is true, then everyone is true, and if one of them is false, then every is false. Consider a square n by n matrix. Let's denote it by capital A. If the determinant is different from 0, then this is equivalent to the following formulations. We say A is invertible. We also say A is non-singular. The opposite is singular. We say A is non-degenerate. It means A has the full rank. That means if it is n by n matrix, then the rank is A. That means that the columns of the matrix A are linearly independent. And so are the rows linearly independent. The opposite would be the case when when the determinant is equal to 0, and then the rank will be less than n. But we don't know exactly how much, but less than n. And the columns and rows will be linearly independent. For a matrix A, we can consider the set of equations Ax is 0. And if the determinant is different from 0, then this equation has the only solution x is 0. Such an equation has always the 0 solution. But when we have the regular matrix, determinant is different from 0, then 0 is the only solution, nothing more. This is equivalent to saying kernel of the matrix A, which is denoted by ker, is the set having just one single element, the 0 vector. So that was for the homogeneous system, and for the non-homogeneous system, Ax is B. Then if A has non-zero determinant, then this system of equation has just one, has unique solution, which can be written as A inverse times the right-hand side of B. Also, this is equivalent to the property that the eigenvalue, that no eigenvalue of A is equal to 0. We will see what is the eigenvalue in the next chapter. And related to the matrix A, we can consider the map, which is a generalization of a function, from Rn to Rn, defined by f at some vector x arrow is equal to the product, the matrix A times the vector. So the matrix describes such a map. And if the matrix A has non-zero determinant, then this map is injective. That means different arguments result in different results. That means the map has inverse, which is described by the inverse matrix. And the map is onto Rn. That means every result, every vector in Rn can be attained, can be achieved by good x, which is equivalent to this equation, that this has solution for any vector B.